going? I'm Noah Wecker. I lead the data team at Stoke. I just noticed that tomorrow officially marks 20 years I've been in aerospace working with data. I've done commercial. Thank you. I deserve those applause already. I've worked with commercial aerospace. I've done defense. I've done space, UAV, eVTOL. Chances are if it flies and has data, I've probably touched it at some point. And I think where we talked a lot about so far low-level solutions, I'm here to talk about and commiserate on high-level problems we all share. This presentation is a little tongue-in-cheek, so I apologize in advance if any of you are offended. I'm a bit of a contrarian by nature, so let's go. Okay, I have an uncomfortable obsession with time series data. What is time series data? So it's where we have data sets, where we have distinct timestamps for everything, and things change over time. Really what we mean is squigglies. We mean squigglies on charts. If we're talking about video, that's not my forte. Video, people are their own form of rock stars, as our images, as our audio is maybe a little similar, but we're really talking about sensor data, and typically lots of it. Time series data in aerospace, how is that different? So a lot of times when we talk about time series data, we apply a timestamp to like some JSON thing, or a timestamp to like some bundle of binary stuff. But really when we talk about time series data in aerospace, we mean numerical values with associated timestamps. What we typically see as our systems get more complex, we start off with relatively simple data structures where we have a single timestamp for a set of numerical values, maybe spanning across multiple sensors. We start to add more components in, and we start to have maybe different sort of timestamps to group different sort of data sets. But the natural progression, at least that I've seen, is that we start to get to more truly distributed systems. We really get it to a point where we have the only really thing we can say for certain is there's usually a single timestamp per data value. So our resulting data shape is relatively simple. We typically have a 64 or 32-bit timestamp. In Stoke's base case, we deal in nanoseconds. We have some sort of identifier, maybe a string. Usually you go like a 32-bit UID, something like that. Then you have some scalar. Hopefully not a lot of strings, you go in enums, but typically some numerical value, maybe a Boolean value, switches on and off, like accelerometers, PTs, that sort of thing. We just have lots and lots of it. And so we usually have one-to-one data timestamp, as I mentioned, as we get bigger and have more systems that are more distributed. A big thing that I've seen in aerospace is typically we want to keep the data forever. Sometimes that's for legal reasons. Sometimes that's for just, going historically and doing analysis. Another thing is we always get told by our responsible engineers is please don't interpolate. Please don't make up data. The only thing worse than missing data is incorrect data. Sometimes when we display it, we have to draw lines between two dots. But at the end of the day, when you're storing data, please don't make data up. And typically, how users want to access this data is they just go, here's an ID or a set of IDs and a set of time, sometimes a condition. Give me the datas. So how does it scale? So typically, our data sets are highly partitionable. So we mean here's a data set with a block of components or for a set of time. So it's, we can partition it fairly easy, mentally at least. When we talk about in the scheme of time series industry and all the things, our cardinality in aerospace tends to be pretty low. What do I mean by that? Well, typically we'll have a system with a bunch of components and sensors, and that thing is most often statically changing. We're not plugging in sensors. We don't have someone out at the rocket randomly plugging in and unplugging sensors. We typically know what the set of sensors are going to be before we operate a test. You can contrast that with things like the IoT space where devices are getting added and removed all the time, or we're talking about application monitoring where users are opening up a browser, new data IDs are coming in all the time and offline. Our cardinality tends to be typically low, which is great. And how we store the data means everything. So whether or not you're going to be in a world of hurt or a world of joy depends on how you choose to store your data. And so as I mentioned, our data sets are relatively simple shape-wise. Well, that looks fun. But on the, how we store it means everything. So typically when you hear someone talk about, oh, we handle terabytes or petabytes of data a day, most often they're trying to sell you something. Because what really matters is not the size of the data. What matters is how many samples per second or how many samples over time. And the reason for that is like if I store, say if I have like a numerical value and a timestamp, and I store that in JSON or CSV, versus storing something like that in raw binary, versus storing something like that and encoding it in binary, saying like, okay, well this this sensor was on 100 times in the last second. I'm just going to send you a numerical value in a span of time. You have very different very different sizes of how that data is stored. So like if I'm going like text, you can easily get to terabytes. Binary can be gigabytes, where if I actually just thought about it, I can store it in something like megabytes. So measuring the scale of your data system by bytes is meaningless without context. So again, someone's talking about, oh, we go through blah, blah, blah bytes of data a day. I shrug. Cool. Tell me about how many samples you're dealing. Tell me the shape of your data. How are you encoding it? And so on. So if our data is so simple, right? Simple shape, highly partitionable, why do most of our solutions sort of suck? I think everyone here has experienced the pain of trying to figure out how to get data to a user and getting just lots of frustrations and figuring out how to store it and how to serve it up. So I'm going to tell you a true story, but it's not really true. So this is an aggregation of a lot of my experiences over the history of my career. To protect the innocent, some of the details have been changed. But this is all stuff I've gone through in my career, and maybe some of you had too. As I mentioned, I'm not here to bring you knowledge. I'm here to commiserate on pain. Okay, so here's a story. First day on the job. Maybe it's a big company with a new group. Maybe it's a startup. But you're testing a single system. You have a single component. It's running at maybe 20 hertz. It's outputting some numerical data, a few sensors. The users click a button, maybe record some data, runs a script. Users want to search and explore that data across runs and tests. They want to integrate with third-party tools. Maybe they got some MATLAB, some LabVIEW things, what have you. There's also this guy on the job. Now, this is not to say that age makes you a curmudgeon. This means that there are wizards out there who are experts in their domain who can also code. And they are wizards. They really are. Because if you can code and also know how to do rocket stuff, kudos to you. But they typically build something like this. They'll have a data file. Maybe they wrote something in C or Python or God help you, Fortran. It outputs some files they put on a server share, and they pull it up in their third-party tool or maybe something they built in-house. And they don't know why you're here. Everything is fine. Please leave me alone. Please don't break anything. So we are superior beings in the data space. We can do better than that, right? So what's the first thing we do typically is a database. That's a word I heard in college. I'm going to build a database. I'm going to throw the data in there. I'm going to add new data tables for maybe systems or components or time spans. New system, new table. I'm going to write a nice, like, beautiful web API or maybe some plugins. And things are great. Things are simple and efficient. I can run SQL to grab the data. It's easy to grab the data we need. It's easy to search for things we want. Like, tell me all the times this sensor exceeded this threshold. We're using Postgres. We've got something that looks like this. We are rocking and we're rolling. But then, our use case evolves. One component turns into multiple components. We have multiple DACs. They have independent sample rates. Maybe they're started at little offsets of time. Our acquisition rate necessarily doesn't equal our cycle rate. So we have a cycle maybe and we're acquiring data at different rates. Stuff's coming in. We have a handful of 1,000 hertz sensors. They're starting to get like a little more higher volume data. There's problems start to arrive. So we have very sparse tables, meaning that I can't just go with a single column for timestamp. For this timestamp, maybe I don't have a data value for some sensors. And our users are saying, please don't make data up. I want to know actually what happened. I have a lot of nulls. Storage starts to balloon, right? So we start to get these 1,000 hertz PTs. Databases start to grind to a halt. There's a desire to add even more data. We're hearing things like kilohertz, maybe even megahertz, words that make me lose sleep at night. Our users are getting frustrated. Our tables start to look like this. We've just got tons of nulls. It's very sparse, and this sucks. We're not having a good time. But wait, we can innovate. We can use skinny rows. We can play some games in the database, right? We have 3 columns. One's for time, one's for ID, one's for value. Maybe we can't intermix types. We got a table per type. We got floats, we got ints, we got strings over here. Our primary key is our ID plus timestamp, and we throw in some join tables. The things seem better. Insertion performance is pretty good. We can select a measurement by time range. Isn't so bad. Maybe I got to do 3 different things from a couple different tables. Starts looking like this. It's pretty good, right? There's no nulls, no sparse stuff. It feels good. But then our use case evolves a little more. We have more data. So I mentioned those bad words of kilohertz and megahertz start coming to roost. We have lots and lots of data. We're having longer recording sessions instead of hitting a button for a couple of seconds. They're doing 5-10 minutes. We hire data scientists. They have new query requirements. So they want to do hey, I want these 4 measurements, all at the same rates. I want to do min, max, or interpolation down to the nanosecond level. Sometimes it's last value, sometimes it's min, max. But we want to take 3 measurements at disparate rates and kind of frame them up and serve them up so it looks sensible on a squiggly graph. We want moving aggregates. We want windowing, all the sorts of stuff that our data scientists want. We now are throwing in 24/7 streaming data. Say we have things that are measuring sensors that are not just when the user hits the start and stop button. It's coming across 24 hours a day, 7 days a week. In case things go boom, we can figure out what happened. And so we start to hit new problems. Our new queries are either impossible or just crazy slow. Indexing starts to use a lot of space. We're smart data people. We're we'll do indexing on this thing, and then that just balloons up the storage space even more. Our selects and insert performance start to get really bad. Our users are, again, getting frustrated. So we have to do SQL queries that look like this, except I have measurement 1, 2, and 3, and I want them at 10 hertz. We have to write crazy SQL queries that I don't think the inventor of SQL ever intended us to do. This sucks. We're back to being where we were before. But wait, let's let other people innovate. We hear about these things called time series databases. We hear about things like Influx, timescale DB. That seems like we have. Let's use one of those. Queries seem SQL-like. You can figure them out pretty quick. They're easy to start up. They're columnar, meaning instead of going through all the rows, I can just grab a column of data and work with it. It's amazing. They have amazing compression. We're hitting something called the Shannon limit, where some of our data sets compressed to 95 to 97%. It's amazing. Our storage space requirements are solved. There's no dependence on tabular data. We can have different rates. It all just works beautifully. With a bit of tweaking, we can get pretty good write performance. We can write all that data. Maybe we have a couple of threads. We have a couple of sockets open. We can do it. Everything seems to be rocking and rolling. And the cool thing I mentioned about timescale databases is that they're meant for time series data. That's what they advertise at. That's what we have. Everything should work. But then our use case evolves again. We have more data, more users, more systems. We got that VC funding, or you got the corporate bear hug from up top. Now you get a bigger group. You got more people looking at your data. You have more data coming in. We have thousands of measurements. We have, again, we get to 100 kilohertz, maybe those megahertz numbers, but just lots and lots of them. We have multiple systems spanning, across the company. Everyone wants to throw their test data in there. We have new requirements. So there's the streaming data retention, that 24/7 data we need to also keep forever. How do you, stuff coming across, keep it forever. Allow users to access it whenever they want. We have new types of data access. People want to do okay, I don't just want, maybe aggregates or time windows. I want to grab this big block of time for all measurements, or I want to, do stuff across multiple tables. Problems start to arise. So these time series databases are great, but they all kind of have HTTP endpoints for writing and reading. Those become bottlenecks. HTTP is great. HTTP is horrible, depending on the use case. There's no bulk import or export. We throw these things in. They're kind of behind a lock and key. If I want to just hey, I have this big giant file. I want to get it in. I can't just do that. I have to go over an HTTP connection. If I want to get stuff out, it's there. Why can't I get it? Well, HTTP connection. You have to construct SQL queries and wait. People want their data sets because they want to do stuff like data marts. They want to cache them in browser. They can't do that. Stuff takes too long. They're getting the little spinny wheel. Hosting costs start adding up. So a lot of these things require an EC2 instance or a server somewhere, a server running somewhere. Anyone that wants a new instance has to have one of these things. How do I stand on one of these things ad hoc? Joining them in a single instance starts to add risk to other people's systems. There's no easy way to integrate with COTS or free open source technologies. We have to write all these custom time series queries type stuff to type of tools that people want to use. Start having to write lots and lots of our own code to do really basic things like grab data, export data, process data. Our manager's getting frustrated with us. But wait, we can use a SaaS. So we don't need it. A lot of these things have managed stuff on the cloud. We'll just throw that in there. There's lots of options. There's AWS TimeStream. There's industry-specific options. There's Influx Cloud. We create an account. We go on. It's super easy to do. We put a credit card in. We swipe it. Everything's good to go. It's easier to set up than it was locally. We started to have the same problems as we had before, except now, instead of even being on our servers, it's running on the cloud. So writing, reading are even more time prohibitive. Integrations, same issue. We have features we want. We contact them. They're like, oh, that's on a roadmap for Q3 2027. We have no influence, no ability to kind of like customize it to our needs. And then we get the bill. And our manager informs us we're going to bankrupt the company in 6 months. This sucks. But then our manager hires this guy. And I want to say, I mentioned I have 20 years experience of aerospace industry. This joke I made up is the single greatest achievement in my life. This guy, he has the data engineering mullet, business logic in front, Parquet in the back. Please use it, get the word out, it's hilarious. We do data engineering, right? We got Parquet stuff, we got S3, the clouds to the rescue. It's a columnar-based binary file storage format. You can do the same sort of encodings and compressions that all these time series databases do, except instead of having to stand up our own compute instance, we can just use S3, which is super cheap. It's got good compression. We can like use all these things to batch and stream data and write it to files. We can leverage and integrate existing services that are already built for us and have tons of high availability. There's like Athenas, Kinesis, glues, sparks, icebergs, deltas, lakes, all these cool words. Our manager's happy. He's like, you're using industry tools. We're not having to handle anything. And our diagrams look like the stuff we read on software engineering blogs, right? Hooray. We did the thing, right? We're in data nirvana. But we're back to day one problems. Why is that? Key issues. Parquet files are tabular. You can do nulls, but then we're back to the sparse problem. They can compress, but then our read performance, our write performance becomes problematic. Tooling is SQL-based. Now to do the sort of thing we talked about back in relational databases where I want like, hey, these 8 parameters that are at different rates all sample at the same rate, we have to write crazy SQL queries. Except now we have 100 times more data, required feature parity with what we had before on time series databases, performance expectations now on read and write, and we have the sticker shock of using services if we use them incorrectly. We're having to write our own code. We go back to like, we can do the skinny row thing versus the fat row thing. Can't we just compress the nulls? Sure, you save on storage, but then your read performance and your write performance becomes super problematic. We explore new options, right? We use, okay, what if I have like a single file per measurement and test? What if I do things like, what if I do things like have a single file per measurement? How do I append these things? I'm having to recreate. And we feel like, hey, what if, did I just reinvent Hadoop? All the stuff from like the early 2000s that we all kind of threw out and said was bad. We have now like a billion files, and finding those things, writing those things just becomes insane. It's hard to manage. Our team is small. We don't know what we're doing. We have now this cloud stuff. We don't have visibility. We've just compounded our problems and made them extremely more difficult. This guy feels completely validated. He's been chugging along the whole time. He's got his files. He brings in, he puts on a Windows Server share. He knows where they're at. He accesses them. He's still like, what are you doing? You guys are just wasting money. So if our data is so simple, why do most of our solutions sort of suck? Databases suck. Time series databases suck. Time series SaaS products suck. Cloud services suck. Parquet tools suck. And I want to say, again, this goes back to the basis of our problem: high speed, asynchronous data. If your data does not fall in those categories and you are happy, please ignore all of this. Keep rocking and rolling. This is mostly talking about high volume asynchronous data. It becomes very problematic. There's overlaps between us in fintech, oil and gas, automotive. A lot of these people share these same types of problems, but I feel like it is unique to high volume asynchronous time series data. This is the end? Maybe. I mean, I'm with Stoke Space, right? Kelly showed you how fast we move. We have data needs where like a test gets done. We have engineers need to be looking at, analyzing, exploring the data within seconds to a few minutes. So we're doing something. So what can we do? And I'd love to come back sometime and talk about our more formal solutions, but there's some first principles here. So first is befriend and apologize to your gray peers. We're optimizing for the wrong problem. Everyone starts with like, let's do something with AI. Let's do something with data analysis. If you optimize for that, you're going to have a bad time. the first thing you need to do, and it's the reason why embedded databases like DuckDB and SQLite are so ubiquitous and popular, optimize for data exploration. How long does it take a user to show squiggles on a screen? If it's more than a second, something is wrong. It should take milliseconds, maybe hundreds of milliseconds. That's fine. But it should be, I want to look at these squiggles, I can see the squiggles. Once you're done with that, optimize for write performance. Your data is only going to get bigger. You're only going to add more stuff. Make sure you can write stuff as fast. If our users are waiting for hours for data to show up, you're doing something wrong. You should be able to, and if you solve that, streaming becomes easier. If you solve all that, again, as you scale your data, your users are going to have a better time. Optimize for programmatic access. Make sure that users can write Python code. If it's HTTP, that's fine. If it's something else that's more optimized, that's cool too. But make sure your users can access your data programmatically and not have to go through a third-party tool, a SaaS tool, or your tools. And then once that's all done, because typically you've optimized for a single node, you're using S3 most likely or something like that, the bulk analysis and the AI stuff is easy to do because scaling a single node on the cloud is easy. It's easy. It's serverless. It's Kubernetes, whatever you want. But that's where the compute can only be when you absolutely need it. You've optimized for the right things. If you start optimizing for bulk analysis and AI, your users are going to have a bad time. Make peace with the fact you're going to have to write some low-level code. What I mean by that is there's a lot of native programming languages out there. You can write stuff pretty easily nowadays. If you want to access Parquet directly, you can do Rust, you can do C++. Using those performant languages to do some of the heavy lifting is something you have to make peace with what you're going to do. Not everything can be Python and Java. There are real implications of performance when you go with those higher level languages. Now you can have Python bindings. I think someone told me once that Python is just organized C. You can write the lower level stuff and have the nice bindings on top. Maybe that's part of your programmatic access. But make peace with and hire the right sort of talent that can do that sort of thing. And then get your Parquet hands dirty. Parquet is horrible. Parquet is awesome. So the Parquet you can do anything with. I would argue there's probably not any type of schema you can't do there. Now the tooling to access that typically requires a tabular format, but it doesn't mean you can't utilize some portion of that if you get creative with the schema. And you can get some of the things along with that with compression and coding. Be very wary though if you start requiring additional indices or you have a lot of nulls, because that will impact your read and write performance. So that's what you can do on an individual basis. What do we need as an industry, in my opinion? We need better open source and file standards. Mr. Moody, you're hearing this, please, MIT license Sun and WinPlot. We love it. We use it. It's a good format. I just want to be able to use it and be able to integrate it with my tooling. Make sure it's columnar with different row sizes. So there's a lot of good stuff out there with columnar, but we need to be able to handle different row sizes. So that's the one thing, the limitation I think of most tooling out there right now, and is counter to the nature of our data, which happens to be asynchronous, a bunch of different rates. Maybe I'll get 1 sample per second. Maybe I'll get 1 million different offsets. Something with compression and encodings, time series data compresses and encodes really, really well. Anything that you're using should have that right out of the box. The ability to append. How do we do things? We have data sets just constantly. Very rarely do we need to go and actually insert. If you do that, I would push back on the use case. Just have it be immutable. If you need to redo a calibration, you should be able to reprocess the whole thing. If you've optimized for a single node, you should be able to do that fairly quick. But to be able to append with having to recreate the entire file is also another thing that I think critically we need from open source file standards. And then document integrated. There are open source and MIT licensed standards out there. They're just, no one really knows how to use them. They're not documented. They're not integrated with tooling. More of that. And then, software components instead of SaaS. We need better Legos. So there's a lot of really cool, really exciting new SaaS products coming out for time series data, specifically in our space. But at the end of the day, you're just giving your data to someone else and you're putting it behind a lock and key. We need better building blocks. I love Influx. I love Timescale DB. Those are really successful because they're really easy to use building blocks. But we need those to be a little more optimized for our industry to be of use when we hit our data at scale and speed. And again, be wary of things that only give you HTTP access, because if it's only HTTP access, someone else owns your data. And then we need more people thinking about the problem. So again, I've spent 20 years thinking about this, working with this. I think from what I hear in the industry, a lot of people have this same problem. We should all be thinking about this more, looking at it more, working on it more, talking about it more. And with that, thank you. Yeah.
Thank you so much, Noah. All right, we're going to take one question because we're a little tight on time, but any questions in the room?
I didn't know whether to laugh or cry.
Hey, I hear I'm Zimri, Firefly Aerospace. I hear you on the Influx Hate, and I hear you on the Parquet Love. Influx 3, I think, is based on Parquet. Any thoughts on that?
Yeah, so there is there may or may not be a Slack thread on that when they were deciding to go to Parquet, where I berated them for the format they chose. They do it. So I think I'll say this: if you're at a certain scale point, Influx or Timescale are really good fits. Influx 3, they rewrote it all in Rust. We don't use anything, I think, greater than 2 for performance reasons. So they changed the way that they format their data. They may have made that better. It may be fixed, but I know when 3 was initially released, there was I think people were seeing 10x degradation in like read performance. It just really comes down to they are optimized for high cardinality and really that IoT and application monitoring space. So when, if I want to add a new sensor, I can automatically adjust that and I can search across multiple things, not necessarily as optimized for us. The Parquet archival thing is super cool. So you can set up to just archive data in Parquet after a while. It goes with the tabular format and there's tons of nulls. So like if you've ever done a query in Influx where you go, hey, give me these elements. I don't want you to fill in anything. You'll get a return table that has a whole bunch of nulls. That's how we're storing it in Parquet. So it may have changed, but that's my understanding. So if you have data sets like ours, where you have 64 kilohertz stuff all the way down to like 1 hertz stuff, and it's all coming in different rates, that's a lot of nulls. And being able to access that data in a reasonable fashion, where I want to see the squigglies really quick, becomes kind of tricky. That being said, it's pretty amazing what they've done. And again, if your data is at a certain scale, I would highly recommend you use it because they're awesome.
Thank you so much, Noah. Round of applause, everybody. Thank you.